Okay, we're going to start the training, and this takes a while. This system is pretty fast, but you get a picture of randomly sampled some of the cats. Bring that into view, and notice that I'm closing that window to let it continue. It'll stop at the point when it displays stuff, and the program you're going to be running also does the same thing. And then some dogs. Now, the dog picture is a little bit different. You'll notice it's the same dog, but the picture's actually been convolved. What I mean by convolved is flipped, rotated, scaled, things that make it look less like a single picture that it's training on and allow the system to pick out features better. The process of doing this convolved on the pictures prevents you from training for a specific item, and with 2,000 pictures that it's going to go through and train on, you get a much better result. Now, before we get done with this, it's going to give us a graph that shows us the results of the training. And this is 2,000 pictures. It's a very small set, even though I get 5 pictures for every one of these. And at the end of it, we'll get, if we're lucky, 70%. Then we'll actually go through and run a test of this against a test data set. So we've got an original data set that we've taken 4/5 of, 2,000 pictures, and we're training against that. And then at the end, we're going to do an evaluation of the effectiveness using 1/5 of the data. And these are randomly sampled pictures. So if we get lucky on this training set, we'll get a good result. Okay, and I do say lucky because only 2,000 dogs is not nearly enough. When we talk about training for pictures, you're talking about, I know Google image search for cats and dogs, they've used 500,000 pictures of each classified times convolved. But we don't have that kind of time nor computer resources, so we're just doing 2,000. So this is a small subset of the actual data. And I think it actually has the 500,000 pictures up there on the site, but we have picked out a little piece of it. Now, with this little piece, we'll get a result of perhaps 70% accuracy. And then we'll test it with some actual stuff with a dog and a cat and see if we get good results. I don't guarantee the good results. I mean, 70% means 30% of the time it's going to get it wrong. And since I'll try a dog and a cat, it's 30 plus 30 is 60%, so you would expect that at least one of the two answers will be wrong. You'll get a false positive for the recognition. But who knows? Some of the time you get lucky and you get them both right. Some of the time you get them both wrong. So we'll see what it actually does when we try a classification. And who knows? We may get lucky this particular run. This is going to take a while, so I am actually going to switch over to going through the code. And we will come back to this run when we have the actual results. Now, I'm going to... I don't think I can. I can move the image here. Oh, this is actually important to see. This is actually the output, okay, of the layers and how it's built the layers. We're using a pre-trained network that recognizes things, that already has a bunch of layers that are already pre-trained, and we're only training the last layer. So you've got an input network that classifies things, and you can see it cranking slowly through a bunch of things. And as it's going through, it had 85% loss, and it's dropped down to 66% loss. As that loss number drops, that's a good indication of how effective it is at training. If you plateau in the loss, that means that your training is stuck. Training can get stuck for any of a number of reasons. Sometimes the solution to stuck training is you just train it again. Because remember, it's trying to minimize a n-dimensional function. And in the process of minimizing that for loss, it actually is got the possibility of finding a near but wrong answer as well. And there's no guarantee that even if we do get good loss, that we got the right answer. So sometimes, you train it 10 times and you look at what your best results are, and then you're going to start asking questions about how good those results actually are. So a lot of this is understanding the data and being able to go through the data and pick stuff out and understand the data. In any case, this is going to run for a while, so we are going to switch over here to a different screen, let that run, and start taking a look at the code. That thing will get done somewhere during this lecture, and it'll pop up a screen, and we'll take a look at the results. So, this particular example is from the TensorFlow site, and I've actually, on the TensorFlow site, it has the libraries, it has an example of how to use classification. It walks you through this, although I have modified the code a little bit so that it works for my system. And actually right there, it popped up the results. And let's take a look at the graph for the results. I've actually had it graph the accuracy as it's comparing stuff, and you'll notice that its peak accuracy was 67% this time, not even 70, and then it dropped off after that. That probably indicates that it hit a minimum and then it went too far, and I haven't done enough training cycles to get it to come back. I would say, looking at that's probably going to be a rather weak training result. Not the best. I mean, we're 65%. Not hugely successful. When I train this on real data, and I do use this software for real data, I'm looking at 200 to 400,000 images of a specific thing that I'm trying to recognize and classify. And they're not little tiny images like this. You'll notice the dog was not a real crisp image. So training for real data means real computation power. And that's why I have a computer that has multiple GPUs in it. And I'm not put off by running a training set for something that runs on my system with 4 high-end GPUs for a month straight in a single pass for training. If I had deep pockets, I would get hardware, and that month would drop to 3 or 4 hours per training round. But even so, you're still talking about hours of training, not other things. The other thing to look at is the training loss. You'll notice in the very first one, it gained a lot in the loss. It started out high and dropped rapidly. After that, the losses continued to drop. Now, suppose that you see something where the loss drops and then it plateaus. Okay? That tends to indicate that you've got problems where you don't have enough data. And we haven't run enough training rounds here to really, or a large enough data set to see that kind of a thing. But when you see any kind of a plateau, then you've got to start asking questions about, do I have enough data? How have I handled the features in the data? Have I looked at how they're encoded and what I'm doing? Why did it plateau at that level? And can I get a better result? Because 60 on a loss, 0.6 is not very good. And I would hope to get the loss down for realistic data to 0.03, maybe, for realistic data. And certainly things like self-driving cars, you have to get a long ways past that point. We don't want self-driving cars that have a 3% kill ratio of drivers. Let's put it that way. So that kind of training requires a lot more data than this. And when you look at something like Waymo, you have to put in perspective that they have 140,000 cars that they have been driving for 3 years in Phoenix. And during those 3 years, those cars have had sensors on them to collect data for Phoenix and for driving. And they collect terabytes of image data a day, times 40,000, times 3 years. Plus all the other data with, every Google street car in the United States driving down every street, taking gigabytes of images a day, every day for a decade. And other sources of data. Now, somebody like Tesla, the big change that they're going to see is 5G, because they know they have way more data coming off of their cars than what they're getting that they can use for training. I mean, way more, like 10, 20,000 times more data is being thrown away than what they can get access to. But with 5G, they can actually transfer that data from the cars back to their mothership, basically, where they can get access to it. The difference for this is that Google, in the way they're doing it, they actually have the cars show up at a fixed location, and they hook up a network to the cars right there, probably wireless, I must admit, but it goes on an actual wireless network instead of trying to transfer the data over cell data. So they use a high-speed network to transfer it. Now, stop for a moment and think about the volume of data we're talking about here. And, we're talking about tens of thousands of images every second, okay? From multiple different perspectives, from multiple different sensors. Tesla is just using visual. Waymo is using both visual and LiDAR, which is laser distance data, and combining it. Some of the others, like GM's driving unit, I can't think of the name of it, their self-driving unit that just announced that they will go live with their full self-driving cars in California next year. They're using visual data, heat data, as in infrared visual data, and radar data. Okay, so they're using radar instead of LiDAR. So some of these things have a lot more data than you and I can see. You know, the joke is kind of this. Their day is going to come when you drive in a self-driving car, and it may be one that you can still control, but the weather outside will be nasty, it will be snowing, and you will be safer to let go of the steering wheel and let the car drive through this than have you drive through it, because it has GPS to tell if it's still on the road in the right place, it has radar to detect obstacles, it can do things you can't do. And consequently, that day is coming very, very soon, within 5 years, at the outside, in my opinion. Now, this is a huge social change, but you look at this data, we've got some results, and it's getting better. This could have used more training passes than what we gave it, but let's take a look at the training. Actually, I have to close this window so it can continue on to the next thing. And it finished the training. Let's now run a test. And the effectiveness was when it trained on 80% of the data, left 20% off, and then it took the 20% and ran all of those as a model and saw how effective it was. And that was the 67% that it was using for our results. Now, let's run. There's 2 pictures in here, a cat and a dog, and I will run predict, and we'll see what our result is. It would surprise me with 67 if it got it right. It got 1 cat wrong and 1 dog, or no, it got cat right and the dog wrong, which is a pretty normal result with 60%. You would not expect it to get both of them right. You know, this is the results that you're going to get if you have small sets with only a couple thousand images. Now, when we talk about doing something like this for being a pickle picker, we're talking about being able to go in and take images for 2 months and have several million images to train with, and other data like weight data. And when you talk about something like, I've been working on a project with bees for a number of years to detect these mites on bees. There's good evidence to indicate that colony collapse disorder in bees has to do with these mites. So if we can take a picture of the bee and identify if your colony has the mites, if, you know, they're on a bee, if we can do something about it, we can do something about the colony collapse disorder. And I probably have a decent sized collection of pictures of bees. I only have 180,000. By looking at my lossage rate, I can tell that I need somewhere around 500,000 pictures of bees to even be in the game. So collecting data for these things is hard. Now let's walk through the code. And I mentioned future, which allows us to do things like division on entire matrices, and an image is a matrix of values. The first thing I do is I check that we're running with the right version of TensorFlow. And the reason for that is there were significant changes between versions of TensorFlow. Either one you can import. If you don't have the right one, then stuff after this doesn't work and you get weird error messages, which is just from having the wrong version installed. We're using a couple different things. NumPy, which is a numerical calculation package for Python, and Matplot. That's what gave us that graph, the line graph. That's going to happen later. And the first thing we do is we go out here and we're going to go out to this location on the web and we're going to pull in this file, cats and dogs. And it is compressed to make it download quickly. If you run this on a slow network, it will still take a long time to download. It is not trivial. And once it is downloaded, then it opens this zip file and extracts the cat and dog information, okay, which is the images. I think the file is about, if memory serves me right, 4 gigabytes of images. So if you run this on a slow network, be prepared to wait, hours for it to download. And this is not the case with your homework, which I am using a much smaller data set and providing it to you. So that was part of the reason why I wanted to switch for homework to doing a smaller data set. And then we split up our cats and dogs into our training and our validation sets. So we're going to pick out things for training and validation and use some for each, okay? Because remember, if we train on the whole thing and then we ask it, is this image a cat or a dog? It's going to say, well, it's a cat because I trained on it. So what we do is we split it so that we've got randomly some that we're going to use for training, some that we're going to use for validation. And it doesn't matter if you, when you randomly split it, if you split it the same way each time. In fact, that's a disadvantage. What you need to do, though, is you have to save some back for validation, or you have to use new data that you get for validation. And I have set down the number of epochs, which is the number of training cycles. That's over here to only 15. We could definitely, looking at that graph, we could have used probably 30 or 40. But even as it was, I had to skip forward in time. And I'm running this on a laptop that actually has an external GPU on it to get this done. So if you ran this on a regular laptop, this thing takes hours to run to do the training. It is not trivial. And then we actually generate the images. And you notice that I set rescale here, and I start doing things to the images. And some of these things that I do, okay, we pick out from the list of file names, we pick out the ones we want. We're going to retarget the size to be image height and image width, because not all the images are the right size. So we have to scale the images, and then we do the sample of it to pick it out, and we have this plot images, which goes through and takes 5 of the images, basically random because they're in a random order, unzips them, and I rendered them. This is where you saw the original set with the cats. So I plot 5 images. Now right there is a list reference that goes from the beginning to 5. And that's our training set sample images. And then we do the same sort of a thing again with the images and take the training data, and we're going to generate a training set. And again, I plotted the images after I'd done some more processing. This was the dog after I had convolved the images. We shuffled them, we did things to them, we did a zoom on them, we did various shuffling on the images, and mangled the images to a certain extent. Now, once we have the set of images, okay, I'm basically going to take the images and train with the different kinds of convolved images. ReLU is one of the different kinds of training things, and you'll notice that we're doing the activation of the images, and then we do this thing again, and we train with them, and we do it again. Each time we're taking the images and we're doing things to the images and manipulating them. And that's the process that we're going to do, is this sequential process. Then we take the model and we compile it with TensorFlow. This is the part that actually takes the model and builds a program based on that sequential set of actions that we specified, and builds the code that runs on the GPU. If you don't have a GPU, it will very happily build code that runs on your CPU, but it will be, if you think the 20 minutes that this ran is slow, try a processor with much less horsepower. You're going to see this same kind of a training thing happen in the other example that I want you to work with for the homework, but it will run even on a slow system in 30 seconds. Even on a really slow system in 30 seconds. So you are not going to be faced with, oh my goodness, it's running for hours and I also have to do my homework for another class on this. It's just going to be reasonably quick. Now, that means that that's a really small data set. It's not a big data set. And this isn't a big data set, but this one is got images. That one's just got some non-image data that we're going to train on. So once we get the thing set up, then we want to train the model. And the model is trained based on a set of epochs. And what happens during those epochs is actually captured with these functions, validation data gen and validation data total, so that we can actually plot it. This is the thing that gives us the plot at the end as to how it did. And finally, when we get done, okay, after we've trained, we've got a range of epochs, which is the set of data that we captured up above, and then we take the plot and show it. That's the plot that gave us the thing with the line graph. So we've got some stuff in here that we're looking at the data to see what it is. That's kind of really important. Nothing is more frustrating than you're trying to train for cats and dogs. You download the wrong data set. You spend hours training on only to find out that your data set is pictures of cars. And you're going, well, that time is just gone. So it's worthwhile having, even in a simple thing, where you check that you're actually getting the right data to train with. If the data is not images, then you're going to have to think about things like, does it have text columns? Am I going to have to change it to numeric columns with a thing called one-hot encoding? We'll cover that in a little bit. But when we get done, okay, yes, after all of this effort and time, I don't want to throw away the model and have to retrain it again, so I've actually done something to save the model in a particular format. Now, the expensive part of this is the training and the work that you do. When you actually run it to test things, it's pretty darn fast. You'll notice that when I ran predict over here, predict ran in maybe a second, maybe less. And it gave me some warnings up here at the top. The data that it actually output was these two lines, and it misclassified it. That wasn't unexpected because this wasn't a real good training run. But at least, it got half of it right. And I actually take the cat and the dog inside the predict. It resizes it to the correct size. It loads the model and it runs it. And it does a prediction on the two images. So in this case, it didn't predict the right thing, but the prediction is pretty easy. And the prediction was not a computationally intensive thing. This is how a tool can be written that takes huge amounts of data, takes lots of training time, and at the end of it, you can run it on your phone. And it can do things like identify faces on the fly on your phone, or adjust your camera for the correct lighting. Because once the models are built, even though they're very, very difficult to build, the result is very easy to run and quick. So this is what classification does. And effective classification can be used for all sorts of things. And if you've got a person, especially somebody working with digital data, and that person, when they sit down, they work with digital data, they say, well, this is this. I am seeing this in the data, or I'm picking this out, or I have to separate these things, or I have a process where I can get good data. That's an important step. But I can say, in this process, I want to take things and I want to shuffle them in different ways. Anything like that is subject to this kind of an algorithm and classification. So this single algorithm is hugely important and has lots of applications. Now, this is one of several different kinds of algorithms that they use in neural nets. Okay. There's generative adversarial networks. This one is a convolutional or an ReLU network. So there are different kinds of networks and different kinds of training systems. That depends on whether you have classified images or classified data. Do you have images that you can say, this is a cat, that's a dog, or do you have data that classifies, as in your homework, that classifies the quality of cars as acceptable or unacceptable? That would be cases where you can use some sort of a system where you have pre-classified data. If you don't have pre-classified data and you have to train as you go, you use a different system. And each one of these systems has their strengths and weaknesses. All right, with that, I leave you, and we will pop out a homework that will be due. We have probably 2 homeworks left. We will pop out a homework that will be due here in a few days, but these last few homeworks are going to be relatively easy because rather than have you write a program, you're going to be taking a program and learning how to run it and use it, and I'm going to be asking you some questions about the code, not implementing the code. All right, we'll catch you later.